Hi, Mrs. Stanley here. Let's talk about verifying inverses. The objective is to verify inverses graphically and algebraically. We will start by doing this graphically. So let's first just write out what is the process to do that. How do we know by looking at a graph if two functions are inverses? So here's the description. Two functions are inverses if they are reflections of each other in the line y equals x. So let's first remember that y equals x would be this line that goes right here diagonally across the coordinate plane. Okay, so let's look at this first one. We should be able to graph relatively easily on our own because it's a linear function, 3x minus 6. So we know the process to find the inverse. We just replace y and x. Remember, this is y. So we would have x equals 3y minus 6. And then we got to get y by itself again. So x plus 6 equals 3y. Divide by 3, and we get x plus 6 over 3 equals y. And that's going to be harder to graph, so we need to simplify it. It's 1/3 x plus 2 equals y. So we have two linear functions. Do we see any domain restrictions? If you think about it, it's a linear function, both of them, so there's not going to be a domain restriction. So let's go ahead and graph 1/3 x plus 2 equals y. Since I wrote the equation in purple, I'll do it first and use the purple color to graph it. So it's going to have a y-intercept of positive 2 and a slope of 1/3. So I'm going to go up 1 over 3, up 1 over 3. Let me plot enough points that I can connect it here on my screen. So here's our line connecting these points. And then I will change colors to graph the original 3x minus 6. So we have a y-intercept of negative 6. 1, 2, 3, 4, 5, 6. And a slope of 3. That means we're going to go up 3 over 1. Up 3 over 1. Up over 1. Up 3 over 1. And sometimes it's actually a little bit hard to see when the graph is so small, the coordinate plane is small. But can you tell, if you look at that black dotted line, that if you were to flip the orange line across the dotted line, you would get the purple one, and vice versa? That's how we know that these are inverse functions. Let's go to number 2. It could get a little bit difficult to do this without a graphing device, so I would recommend for you, for example, desmos.com, or if you have a graphing calculator, it will help you to find some points to be able to plot easily. So let's first look at f of x equals x cubed plus 4. We don't have any domain restrictions on that because it's just a cubic function. It's a polynomial basically, but we can go ahead and find the inverse function. So we would have x equals y cubed plus 4. Solve for y. I've got x minus 4 equals y cubed. Take the cube root of both sides, and we get the cube root of x minus 4 equals y. Are we going to have any restrictions on this one? We aren't. And I just realized, I'm sorry, there's one thing I left off on number 1. Go ahead and write your equation using the inverse notation. We should have done that on the first one, so I'll go back and do it just so that we have it correct. Ugh, I wanted that to be purple. Okay. The inverse function was 1/3 x plus 2. That is required. Write that on your paper. You notice that I forgot, so you're going to have to be careful to make it for yourself, to remind yourself to do it. That's why we're going to remind ourselves, so that we get this habit of doing it. So I have a cube root of x minus 4 and x cubed plus 4. Let's look at this on a graphing device. So if you haven't used desmos.com, this is what the website looks like. We can go to Math Tools and go to our graphing calculator. And over here, I can actually apply insert my two functions. The first one was y equals x cubed plus 4. So I have y equals x to the power of 3. To do a different exponent besides 2, you use this one, and you'll see it went up there. And then kind of arrow down, plus 4, right? X cubed plus 4, yes. And then I can hit enter to get another graph. And you notice it does this nice thing where this one is red and the graph is red. So that's great. And so the other one is that y equals the cube root. So this time I'm taking a cube root, which if you don't know where something is, you can also look on functions. let's see, here we have an nth root, so that's going to be 3, and then you got to tap to go underneath it, and underneath it's going to be x minus 4. So this is our graph. Notice we've got a red one and a blue one, and I'm going to go ahead and add in here y equals x to be the one that we're looking at reflecting over. So let's look at this. You see the red and blue one, and think about the green one. Am I reflecting over the red and green? And I am. Now, if you had a graphing calculator, it would be very easy to just look at the table. On Desmos.com, you can also see these functions. We don't need the green one, so if you wanted to tap on the green, notice it goes away if I tap on the graph there. Okay, and it'll come back. But so I'm going to take that away to focus just on the red and the blue, and you can just find some points. So for example, if I tap right here, I can tell there's a point at 0, 4. And so I can use 0, 4, and actually you can see these lovely points, 0 and negative 1.587. You could estimate the intersection is pretty close to negative 2, but that doesn't help me. I need some exact points. So looking right here, you can see this is like negative 2, negative 4 if you get right on it. So I know we have 0, positive 4, and negative 2, negative 4 on my red graph, and that would be one way to connect it. Let me just show you 1 second. Let me show you how you can make the function into a table. So if you come up here to settings, you can click on this one that says table, and then you can see some actual points. And the nice thing is you can pick out the ones that are good whole numbers, like negative 2, negative 4, negative 1, 3, 0, 4. These are the points that you could plot. Because remember, on our worksheet, we need to actually plot the points, okay? And you can see here that you can do it for each of the functions, and so I can now see a table for both of them. And you can see on the blue one, it's a little bit harder because I don't have any nice solid points there. So we can look at, well, how can I change that? You can see that the tables are making the x values match, but this isn't helpful on my blue one. So I can come over here and say, well, what about if x is negative 4? And so I can type in here if I want to change it to a negative 4. If you tap at the bottom, you can add a point and you should be able to type, yeah, see now I've got negative 4, negative 2. Looking at the graph, we just need a few points. What's another one right over here? 4, 0, which we can see if I put 4 in there, I get 0. You could look at any other points that are going to help you to graph it. Maybe what is this one? Well, we already know it's 2 and negative 1 1/4 because 2, oh yeah, 2 is on the table right here. Right here at this one, 2 and negative 1 1/4. You just need enough to be able to draw a basic graph, so you can choose whatever is helpful for you, and then we will go back to our other screen to actually draw the graphs. So back here on our screen, I'm going to draw the blue ones for the inverse. So that's our cube root of x minus 4, and we said we had negative 4, negative 2, so I can go over 4 and down 2. We said we had 4, 0 was way over here. And then we need to try to get the intersection of the two graphs. That will be most helpful. So basically, if you remember, it was kind of close to being like negative 2, but not quite. It's more like right here. Sorry, my computer didn't work there. Oh, I went in the wrong place because I moved my pen. So it's about right here. And so if you think about it, the graph of this particular function came over from this side, and then it curved up like this. This was the blue one. And then for the other one, let me change colors. And we had some easy points on the x cubed plus 4. We had negative 2, negative 4. So when I was at negative 2, I was down here at negative 4. Ugh, I thought I changed colors. My bad. Let me do it again. Negative 2, negative 4 were right here. And then we had negative 1 and positive 3. And then we had 0 and 4. And let's see, let's get on the other side, 1 and 5. That was kind of our curves. And then from 2, it went way up off the graph. And so this one looks more like this. It's coming this way, and then here's our curve like that. So you can see, if you think about that same black dotted line going through this, this would be a reflection, okay? So there's 2 of those. Let's go to the next part, verifying inverses algebraically. Let's see what we need to do for that. Okay, here we go. 2 functions, f and g, are inverses if f of g of x equals x and g of f of x equals x. Notice it's basically the two ways that the functions can be a composition. They both have to be able to simplify to x. So let's look at number 3 as our example. We have f of x equals x minus 7 over 2 and g of x equals 2x plus 7. So let's start with f of g of x. We could take a moment and ask ourselves about the domain. G of x is a linear function. F of x is x minus 7 over 2. Again, there's nothing in the domain that's going to be restricted on either of these, so there's no reason to think that they automatically couldn't be inverse functions. So let's go ahead and do f of g of x. So we've got something minus 7 over 2. The x is what's supposed to be there. Let me rewrite that a little bit neater. I want to give myself enough room. So where the x was, it's now going to be 2x plus 7, right? We changed x for the g function. Well, what's 2x plus 7 minus 7? We can see that the plus 7 and the minus 7 are going to cancel out, and so we're left with 2x over 2. 2 divided by 2 is 1, and we're left with only x, okay? So now let's look at it the other way around. If I have 2 times something plus 7, I've got to put the f of x in there where the x was. X minus 7. I should have changed my color like I did last time. So we'll change it back to the orange. We have x minus 7 over 2. And what's going to happen here? The 2's will cancel out, and I've got x minus 7 plus 7. Well, what happens there? We're just left with x. So both of these are x, and the answer is yes, they are inverses. You see how that happened? They both simplified down to just x. You go ahead and give it a try on number 4 by yourself. Notice that we do have a restriction on f of x. It says if x is greater than or equal to 0, we are dealing with x squared minus 5. The reason that's helpful is because we have a restriction on x squared minus 5, which would normally be all real numbers, but square root of x plus 5 would always be that the square root of x plus 5 has to be greater than or equal to 0. So by limiting both of them having a restricted domain, it is more possible that they are inverses. So let's check them. Okay, so we will start with f of g of x. I'll write it out this time. So we're going to have f, which is something squared minus 5. And what's going to go in there? It's going to be our g. So it's the square root of x plus 5. Well, what happens to the square root and the square? They cancel out, so we're left with x plus 5 minus 5. Plus 5 and minus 5 leaves just x. That one equals x. Now let's try the other one. G of f of x, we get the square root of something plus 5. Well, this is where we come in with the x squared minus 5. So we're going to put x squared minus 5 in here. This is the f function, right? And so now what happens? We've got x squared minus 5 plus 5. Well, the minus 5 and the plus 5 cancels out, so we've got the square root of x squared. The square root and square root undo each other, and we're left with just x. So the answer is yes, these are also inverses. Okay? Okay, there's one more example here, number 5. Go ahead and pause and then come back to check it. So I'm just going to stall here for a moment, so there's no excuse for you to not pause the video, try it on your own. Okay, here's the solution. I think the main thing that could be a potential concern is if you don't know how to deal with these denominators. For example, right here, 3 over 2x minus 1 plus 3, you had to get a common denominator, and the common denominator would be 2x minus 1. That's how we end up with 6x over 2x minus 1. Same thing in g of f of x. Down here, we've got 2 times x plus 3 over 2x minus 1. This time we have to get a common denominator of 2x in order to do the subtraction and end up with 6 over 2x. If you're not sure how to do that, then let me know and I can send you a completed solution or a video where you can see that done mathematically. So when you come down to the next part, we have find the inverse of each function, state any restrictions in the domain, verify graphically and algebraically. So that is important to note that we're going to do both processes, graphically and algebraically, which would be the first two parts of the worksheet. We're going to combine them together. So looking here, the first thing is we have f of x equals a cube root of x plus 2. What do we know about the domain of a cube root? Since the original function has a domain of all real numbers, we should be fine to not have any restrictions in the new function, but let's go ahead and look at it and see. When we switch the x and y, we get x equals the cube root of y plus 2, x minus 2 equals cube root of y. So we take the we cube each side and we get x minus 2 cubed equals y. So that's the new function, and again, this is going to be without any restrictions in the domain. Now what we need to do is go ahead and graph them here. Remember, we're going to graph them and make sure, does the graph reflect over this line that I've just drawn in a green dotted line. And then we're also going to go ahead and do f of the inverse of the inverse of x. And then we're also going to do f inverse of f of x. You're going to do both of those and simplify them and see if you get x. So I've given you a moment here. Since this isn't something new, I will let you check the answers in just a moment, reminding you that you can use a graphing device to get the graph and find some points. If you don't remember how to do that, go back to the earlier part in the video where we did it on Desmos, and we made a table and picked out some key points. And then for verifying algebraically, that's what we just did in the last examples. So pause here, do those two steps, and then check your answer. Okay, here's the work for this one. You can see that algebraically they both simplified down to x. You can see the graphs. I did the original function in orange and the inverse in purple. And so you can see what has happened there. They do look like reflections. You can try the same thing on number 7, but let's first discuss the restriction on the domain and how that might affect your problem. And then we'll also look at 8 and 9 because that also will have restrictions. So on number 7, we are told that we have x plus 4 squared minus 2, and it says if x is greater than or equal to negative 4. This is helpful. When we find the inverse, we'll need to check what is the restriction on that. So let's look first. We would have x, let me get my pen, sorry. We would have x equals y plus 4 quantity squared minus 2. So we would go ahead and simplify. Square root both sides. Square root of x plus 2 equals y plus 4. Last step. I am going to go ahead and write that as the inverse. And then the thing that you need to realize is when you're doing the domain restrictions on a square root function, it's actually going to be whatever is on the inside has to be less than or equal to 0, or I'm sorry, greater than or equal to 0, because remember, we can't take a square root of a negative. So what we're going to do is look at x plus 2 greater than or equal to 0. That means x is greater than or equal to negative 2 is our restriction on the domain of the inverse function. That doesn't necessarily mean that it will affect anything on our graph. It'll just give us an idea of where the graph starts and stops. Because remember, a square root function is like this. So it'll just be limited. It's not going with a full domain of all real numbers. So on the graph and on the algebraic, it doesn't actually mean that it's going to affect anything just because it didn't have unlimited domain, all real numbers. It has a restricted domain. That's fine. Go ahead and do the graph. Again, you can use a graphing device if you have one, and also do the algebraic check. So I'm going to let you go ahead and finish. You need to do the graph and the algebraic on your own, okay? Doesn't mean skip them. I'm just going to give you some talking points about number 8 first. So right here we have reciprocal function 5 over x. So when we find the inverse, it's probably also going to be a reciprocal function, but we already know based on this original function in f of x, x cannot equal 0 because we would have 5 over 0 and that would be undefined. So we have a restricted domain. Let's go ahead and find the inverse. X equals 5 over y plus 2. So we've got x minus 2 and then equals 5 over y. Some people make this a little bit faster by doing cross multiplication, which you can, that's up to you. But if I wanted to go ahead and keep simplifying this, I'm going to multiply by y and then I'm going to divide by x minus 2, and so it's going to end up looking like this. So now that I have my inverse, let me write this as f inverse. I'm not going to have enough room, that's okay, I'll fix it. Now, I've got my f inverse of x equals 5 over x minus 2. What does that tell me about x in this function? Well, x minus 2 cannot equal 0. So let's see what value that would be. I mean, we know it's 2, right? So x cannot equal 2 is our restriction. Now, you're going to go ahead and use these two equations to graph them and see graphically, are they inverses? And then also algebraically check them, okay? Okay, you need to go ahead and finish those. I think I already said that. Number 9, we have a square root function. And so that means that, again, like we had on a previous problem, our domain is restricted. Under the square root cannot be 0. It has to be greater than or equal to 0. And so that means that x is greater than or equal to -3, right? Now, what you may not recall is that in order to find the restriction on the inverse, what we can do on this one is actually find the inverse function and also see, well, where would the inverse function equal -3? Or what is the y value when x is -3? So we're going to find f of -3. Let me change my pen color for that. So for f of -3, we're going to plug it in, and -3 plus 3 is 0. The square root of 0 is 0 times 1/2 is 0. So it's going to be 0. That means when we get our inverse function, the domain is going to be restricted to not being able to be when x equals 0. So let's go ahead and find that function. We have x equals 1/2 square root of y plus 3. So we do times both sides by 2. And we're going to get 2x equals the square root of y plus 3. Square both sides. Okay, so I've got 4x squared equals y plus 3. Subtract 3, and that's what it equals. So if I want to rewrite this with my inverse, I forgot the little one. The f inverse of x is 4x squared minus 3. Now what you might think here is, yeah, but that means it should be unlimited domain because it's a quadratic. But remember, we're only talking about the portion that's going to go with 1/2 square root of x plus 3. This graph is going to be like about a half a parabola. When we limit our domain to 4x squared minus 3 to being that x cannot equal 0, actually, it's not just equal, it's x is greater than or equal to 0, then that's going to also give us a half of a parabola, and so it's going to be making more sense that it is the inverse of 1/2 square root of x plus 3. So go ahead and do the graph, and that will be more visually obvious, and then also you can do the algebraic check. Remember, you do have the answer keys to check 7, 8, and 9 once you have completed them. Okay, thank you.